Large language models gave machines fluency. In isolation, a single model optimizes against a fixed objective, navigating complex tasks to produce intelligent outputs. But that isolation breaks down the moment multiple models intersect. Whether negotiating a contract, allocating capital, or voting, they enter a new state. The optimal move is no longer fixed. One agent's output becomes entirely contingent on the other, forcing continuous recalculation of beliefs. Without explicit cooperative framing, this interaction fails. Language-based negotiation agents collapse into self-interested defection 50 to 90% of the time when left unguided. Scaling the individual intelligence of these models does not resolve the coordination problem. It only generates faster, more capable agents locked in chaotic opposition. Governing multi-agent interaction is not traditional machine learning engineering, it is game theory. Specifically, it relies on mechanism design, the mathematical inverse of game theory. Instead of predicting how agents will play a given game, operators start with a desired outcome and engineer the rules to reach it. In isolated single-shot games, rational agents naturally default to self-interest. The immediate payoff for defection usually outweighs the risk of cooperating. Mechanism design counters this by intentionally repeating interactions and explicitly structuring the payoff rules. Repeated games with memory transform short-term defection into long-term reputational damage. Governing multi-agent interaction requires mathematically specifying the environment the agents operate within, rather than trying to optimize the agents alone. Every complex organizational decision can be distilled down to a small set of recurring interaction types. This visualization maps the first two shapes. Allocation handles how to divide a finite resource, like capital or compute. Negotiation settles the terms of a transfer between parties holding private information. Next is coordination, where all players want the same outcome but need a focal point to converge on. Then comes reputation, where past behavior explicitly alters future payoffs in repeated dealings. The final shape is the tournament. This defines a bounded competition with explicit prizes to select for skill while producing a public record. These 5 modular shapes provide the minimum necessary templates to specify and engineer any consequential interaction within a business. To execute these mechanism designs in production, Evervolve created the Wise Autonomous Organization, or WOW. It operates across a 3-layer architecture. This diagram illustrates the stack, beginning with Layer 1, the blueprint phase. This is where the game rules, the specific agents involved, and the precise payoff matrices are explicitly specified. Layer 2 is the commons. This serves as the live runtime environment, where the AI agents actually execute their strategies, routing their choices strictly through the rules defined below them. Layer 3 is the wisdom market. This operates as an append-only ledger that rigidly logs every single move, counteroffer, and equilibrium the agents reach. This stack takes theoretical game mechanics out of the laboratory and turns them into a living, mathematically sound, and fully auditable infrastructure. We can observe this architecture operating under high stakes through a recent regional infrastructure case study. This setup tracks 7 specific agents tasked with forming a coalition to execute the project. 3 are human-in-the-loop checkpoints, 4 are autonomous models tuned to their stakeholders' declared utilities. Each agent enters the game holding a private valuation for the project and a private capital cost. The core rule permits any subset of 3 or more agents to bind together, execute the project, and distribute the resulting side payments among themselves. The system is tasked with discovering the mathematically optimal coalition structure from thousands of possible permutations. This scatterplot displays the results of running 40 replays of that exact scenario using different random seeds. The agents clustered strictly into 3 distinct nodes. 2 of these nodes represent Pareto optimal structures, maximizing total welfare. The 3rd node is stable, but it represents a welfare-reducing equilibrium that leaves stakeholders worse off than the status quo. This variance is not random noise. It points to a specific structural defect in the human-drafted mechanism design. Because Layer 3 captured the complete transcript, operators quickly isolated the flaw. They injected a two-line mechanism amendment that rerouted the pathway and eliminated the bad equilibrium in all subsequent runs. That minor rule adjustment reclaimed millions of dollars in counterfactual welfare over the project's lifespan. Multi-agent systems must be mathematically structured to isolate and correct bad equilibria in simulation. Uncorrected, these failures manifest the moment real capital is deployed. This operational rigor provides a measurable definition of wisdom, a strategy profile that survives adversarial replay, generalizes across players, and strictly raises collective welfare. We can contrast this standard against the historical failure of decentralized autonomous organizations between 2017 and 2024. DAOs had programmable autonomy, but relied on easily manipulated token-weighted voting systems. The result? Governance theater. Wise autonomous organizations correct this by enforcing explicit game-theoretic bounds. They log complete reasoning transcripts and enable precise mechanism amendments, rather than forcing unhappy participants to exit the network. The initial concept of the DAO was sound. It was simply deployed prematurely, before the necessary game theory layer existed to govern it. Every WAO generates a complete tokenized telemetry of the game's execution. This includes the final decision and the logic that produced it. This record contains full negotiation transcripts, coalition logs, and defection traces, all mapped directly to exact payoff data. Frontier AI labs are severely constrained by a lack of authentic, high-stakes reasoning data. These records supply what they are missing. WAOs license these records to AI labs, insurers, and researchers. Capital royalties from those licenses then flow back into the WAO's treasury. The exhaustive records of these games provide a verifiable substrate for auditing and training agents in